Yeah, so let's get started. Thank you for this opportunity to talk about my project. My name is Fabian Haßlacher, and I did a bachelor's thesis where the project was a collision detection library for games. It was obviously written in C++, and the thesis was supervised by Professor Helmut Lawacz, and it is called the Vienna Game Geometry Library. I'm from the University of Vienna, and I am currently doing the bachelor there at the Faculty of Computer Science. So, okay, I hope. Okay. So, what is the problem I try to address? You need collision detection for games, obviously, how objects are colliding and whatnot. And what do you use for that? There are a plethora of possibilities you could use. You could use a physics engine or a small physics solver. Probably all of you are familiar with Unreal Engine, which includes its own physics and stuff. And yeah, my project tries to address a part of that. The Vienna Game Geometry Library, short VGeo, tries to do pure collision detection. So only the calculations on how objects are colliding and not solving or responding to them. That would be a full physics engine. And it's part of the Vienna projects, which Professor Lawacz already talked about. You can find it on his GitHub, where there is also the Vienna Vulkan engine, physics engine, and a bunch of other projects. Just quickly, the math library I used for this is Terathon Math Library. It's by Eric Langell. This is based on a geometric algebra model, which he developed. Not only him, but plenty of other people. And he did a library on this model, and this was interesting for my project because it's way too broad to talk about this in depth here, but just a quick info that there are obviously 3D vectors and 4D matrices, so the standard operations you'd expect in game engine development. And there's also a wedge product and anti-wedge product, which are just operations to join geometric models or combine them. Yeah, that's all I'm going to talk about that. If you really are interested in this, I'd recommend you check out his work. So my library offers currently in its state 4 shapes: an axis-aligned box, which offers no rotation, a capsule, a polytope, which can be any set of points and faces, and a sphere. And the way I implemented this is through a C++ concept. So the required functions that those need to implement are listed here. So compute bounding volume. This is templated on a bounding volume, which is also a concept. Centroid and support, which is used for the calculations, and intersect ray for providing also not only collisions, but shooting a ray into the scene, so ray casting and that. And to solve the problem with polytopes, because on the left you can see an object I loaded into the library, the Utah teapot, and this is too complex and expensive and honestly not worth it to do collision detection with this in the context of games. So I built a convex hull builder, which the result of that you can see on the right side, how the teapot got transformed. And for this I used a quick hull algorithm. Okay, so creating the system. So you just, everything is managed internally, and you can change some stuff at creation if you want to go deeper, but basically you just create the collision system, which takes a template of the broad face algorithm you want to use, which is selected by default So if you don't want to do anything, this is how you create it. And then you define and add your shapes. So here you can see you define a sphere with a radius. There is a define function for every shape, and it takes the respective parameters. And you get a geometry handle, and this geometry handle is then used through the add function of the collision system and to actually instantiate it. And this yields instance handle. Yeah, and to build, I also provided two CMake options, which is actually double precision to switch from float to double, and with Vulkan, because right now it's not implemented. There are only Vulkan stubs, but in the future it is planned to include a GPU path to accelerate some stuff. And these are the handles. So the geometry handles, they are uint64 bit types, and they use bit shifting and masking internally, and they are used to identify shapes in a basically just a slot map with an index, a generation, and the geometry handle additionally has a type, which is used to identify the shape type internally, and the instance handle is the same, just without the type. And on the right, you can see how an example would look for both of them. So in the geometry, you see the 3 is the type, then the generation, then the index. These are the queries you can do with the library currently. You can query all, which just calculates every possible collision there is currently and gives you the result. You can also just query a pair, so you provide two instance handles and it gives you the collision of those two objects if there is one. And then also a quality of life function is query overlap, which is just the same as query pair, but just as a Boolean query. And you can also cast array into the scene with an origin and then direction. And the results of those queries you can see here. So query all provides a vector with all collision pairs, and the collision pair contains the two handles that are part of the collision and a shape contact, which contains a normal, the depth of the collision, and two witness points, which you can see on the right. These are two boxes colliding, and the two blue points are the witness points, and the separation vector, which would be used to separate those two. And from the ray casting, you also have a ray hit, which is very similar. You get the instance handle and a position of the ray hit, the normal, and the distance along the ray where it hit. Coming back to the broad faces, so if you want to choose which one to use, you can do so via the templates internally. So here you can see the general broad faces, which are also a concept, so they need to provide the same functions again. Index grid and sweep and prune are the basic general broad faces, with index grid also taking a float for the cell size. So this is basically just a 3D grid where the shapes get populated and it only checks against its neighbors. Sweep and prune, where they are put into axis-aligned bounding boxes and spread out with a min and max point along an axis. And then lastly, I also have a refinement of this broad face concept, which is a broad face with a bounding volume. And this is currently a bounding volume hierarchy and brute force. Brute force was initially just added for testing purposes, but I kept it for comparing results, which was interesting. And bounding volume currently is only AAPB, so this will probably be extended to support more of them. And for the narrow face, there is a GJK and EPA collision detection algorithm which are implemented for general fallback. So every time a polytope is part of a collision, this gets used. And in other cases, there are specializations which capsule sphere and sphere and capsule are provided. And on the right, you can see some tests I did, which means when you can use the sphere, it's obviously much more efficient. And I'll also show you an evaluation. This is a testing I did with just querying all collisions. I did it up to 10,000 instances, and you can see actually here that at 10,000 instances, I tested this with spheres on my PC with about 25,000 collisions. It takes about 10 milliseconds. So if you look at that in regards to the frame budget of 60 FPS, it's about 60% of that. And if you compare it to the brute force, which took 190 milliseconds, and brute force is just testing every shape against every other shape. Yeah. And now I'd like to show you a short demo I did with Raylib. Okay, so here you can see the shapes. This is, again, I visualized this with Raylib. And this is the box, the capsule, and the Utah teapot. This is the original model. This is the one I got from the Convex hull builder. And you can move the shapes. This is all done. So the graphics is Raylib, but the calculations is all done by the Vienna Geometry Library. So you can move the objects, you can rotate them, you can scale them up and down. And here you can see the collision detection in action. So it's calculated on the fly. Again, the two witness points, the separating vector. And I'll quickly show you also the ray collision. So this is it. You press R to cast a ray, and it gives you each collision with the shape and the hit points and the hit normals. So concluding this, as I said, for future work, the reason I used concepts originally is because I knew in the future it would probably be extended, not by me, but yeah, additional bounding volumes. As I said, only an axis-aligned bounding box is currently available. More shapes, maybe more broad faces, and as I said, a GPU path with Vulkan to increase performance, and eventual integration, as Professor Hlaváč said, into the Vienna Vulkan engine or this ecosystem. Yeah, that concludes my talk. Here you can see all the info again, and thank you so much for listening. And yeah.
Thank you. Let's get into my slides. Right. So, thank you, Fabian. I also need to tap to my slides now.